Alright, through the magic of YouTube, it's day 3. I was at this till about 10 o'clock last night looking for things. The unit was having a hard time settling down. Now, a Wien-Bridge oscillator uses this lamp in the cathode circuit of one of the tubes. What it is a variable resistor based on temperature. And it's right here in the cathode circuit. And as the amplifier or the oscillator starts to draw more current because the power level's increasing, the filament will get slightly warm, increase in resistance, and lower the power level. Now, the tube never gets anywhere near incandescence. It's just using the filament as a resistor that varies resistance with temperature, and the temperatures are extremely small. You can't even feel it. You know, if you put your hand on the lamp, it's not even above ambient room temperature. But they work quite efficiently. These have been used in multiple units over the years. In fact, that Heathkit unit right here uses the same thing. It's a transistorized unit, but it uses a lamp in the circuit to control the output level. I did a calibration on this using this pot and the trimmer cap so that the output is constant from one end of the frequency dial to the other end of the frequency dial within a couple tenths of a volt. It's surprisingly level across its frequency range. However, frequency tracking on this unit is horrible. At 200 hertz it's off about 80, and when I get up to 2000 hertz it's off about 480 hertz. A lot of these 1% precision resistors have drifted out of their 1% tolerance range. These are the frequency determining resistors or devices in the circuit that are selected by the switch, by the range switch, excuse me. I'm not going to change those. That's up to the next owner. I'm sinking more money into this and capacitors and purchase and yada yada yada. It's not something that's staying on my bench. I'll get the unit working as well as it can work. This won't affect distortion or anything of that nature. We'll try to get the square wave as clean as we can. We'll get the sine wave as clean as we can. As far as frequency tracking, I really don't care very much. For the intended use of this, say for working on amplifiers to look for distortion and testing purposes, frequency accuracy is not a big deal. If it's somewhere within a few hundred hertz, it doesn't matter. These weren't intended to be anything even approaching a frequency standard. They were just for testing audio characteristics of amplifiers. And if you're off a couple hundred hertz, it just doesn't mean anything with the equipment that you'd be working on with this. So if somebody wants to get anal retentive and change those out and try to get this thing to track within 10 hertz across the band, more power to you. To me, it's a waste of time. However, I did find some things that are notable. There's 3 grounding points in here two grounding points and one other connection that rely on hardware. The grounding point, common grounding point here, is held in with a 632 nut and bolt. There's another grounding point right by the lamp that's a 632 nut and bolt, and the connection to the frame of the capacitor is via nut and bolt and a little solder tab, which is an extremely poor way to do things. Over the years, these washers have relaxed a little bit, the fiber washers that insulate the capacitor frame, so this connection was a little bit loose, as was the common ground here and the common ground in this lamp. And that was manifesting itself when you changed frequency. The oscillator would keep bouncing for probably a minute and then get slower and slower, and then it would stop and settle in. And just by wiggling ground points and wiggling this connection a little bit, you could see it affect that stability. And that's caused by the lamp going, warm, cold, trying to find its stable point. It's and it couldn't do it because the resistance was changing on these grounds. So I soldered this tab to the chassis. I left the nut alone. You can still remove the nut and screw. I just soldered the edge of the tab to the chassis here. I did the same thing down here, and I ran a little jumper wire from the tab to the center of the stud and soldered it right to the end of the stud. Now I didn't get any solder on the threads. You can clip the wire and still remove the nut if these fiber washers ever have to be changed, or you ever want to take the capacitor out for whatever reason. It'll be no problem. The solder is only on the very, very flat end of that screw. I just needed a reliable connection there. Now when you change frequency, it bounces about twice and it stops. It settles right in. And that's a characteristic of these oscillators. When you change frequency quickly, even the solid state Heath Kit one, you'll see the output meter do a couple of wiggles and then settle in. They settle in after a couple of bounces. Perfectly normal. Then I decided to see where we're at. We've got all of the paper waxies replaced. We replaced one of the electrolytics here and the leaky electrolytic on the output, mainly for safety reasons, just so that you don't have any voltage on the output terminals to do any damage to anything you connect to it. The level was low there. I don't think it can get above, let's see, 60 volts would have been the highest it could have reached. It might have given you a little tickle, but it certainly wasn't dangerous. But it'd be dangerous to a solid state amp that was DC coupled. At any rate, I decided to take a distortion reading and was pleasantly surprised. Right now it's sitting at 3000 hertz. And up here is the distortion analyzer, and I can zoom in on that a little bit. There we go. That is sitting, where's my other pointer? There it is. Right now we are sitting at 0.3% distortion at 3000 hertz. The way these work, you inject a signal of a known frequency or whatever, and you set the level so that it's full scale in the meter. That sets a reference point for as far as level goes. Then you tune this to notch the fundamental. That is, this is an extremely sharp high Q filter, and you tune this to the fundamental and it notches out the fundamental. In other words, this is at 3000 hertz. This will remove 3000 hertz. It notches the 3000 hertz completely out of the signal. Anything that's left is distortion, harmonic distortion. So once this is notched, whatever is left from the original signal, that ratio is calculated and it gives you your distortion figure. Right now it's sitting at 0.3%. Now this unit is rated at 1%. And I'm on the 1% scale, so if it was operating at its worst, at its 1%, it'd be full scale. But you can see the needle is sitting at 0.3%, which is pretty amazing for this piece of equipment. We have two more filters that we haven't changed yet. We have a 20 microfarad here in the square wave generator, and we have an 8 microfarad in the square wave generator. What I'm going to do is set it up for square wave, and I will bridge this with a second capacitor just to see if it makes any change in the waveform of the square wave, and I'll do the same to the 8 microfarad and see if there's any improvement. Now I have caps ordered coming in. They'll be here in a couple of days, but I'll in the meantime bridge them with a second capacitor here just to see what kind of improvement we can get on the square wave. As far as I'm concerned, the sine wave portion of this thing is fixed and running. Okay, this is our square wave at 20 kilohertz. Notice the rounding on the leading edge. And yes, I am using a properly compensated oscilloscope probe to look at this. So there's 20 kilohertz. There's 2 kilohertz. That actually doesn't look too bad. It looks pretty good. And this is 200 hertz. Notice the slope. As far as I'm concerned, that's going to be fairly normal for such a simple square wave generator that is capacitively coupled between stages. This is not a Macintosh, not a $10,000 DC coupled Macintosh. This is a single 6SN7 capacitively coupled between a pair of 6K6s. And quite frankly, that looks pretty good to me for what this simple circuit is. Now you might be saying, what about those electrolytics? I'm betting they make no difference whatsoever. So let me bypass them, or let me put another set of caps in there. I will temporarily use my $6 electrolytics just to see what happens. Alright, we have bypassed the 20 microfarad and the 8 microfarad. I've got a 10 microfarad, but that's close enough. The 20 microfarad is the cathode resistor on the 6SN7. The 8 microfarad couples the output to the cathode follower. Between those two electrolytics, the electrolytic that couples into the grid on the 6K6 cathode follower and the electrolytic on the output, seeing a slope at 200 Hertz is not at all a surprise. There's going to be some time constant involved with all those electrolytic capacitors in line. So there's our 200 Hertz, indistinguishable from what we had before. There's our 2 kilohertz, still looking fairly decent. And here's our 20 kilohertz with the leading edge rounded out. Now you could play with this thing until Christ came for a second visit, and I don't think you're going to make much improvement at this point, and I consider this diminishing returns. This is perfectly adequate at 2 kilohertz for amplifier testing to see if you had any serious high frequency roll off or any serious low frequency roll off. You'd see if you fed this into an amplifier rounding off here or here depending on the amplifier characteristics. And again, nobody's going to use this thing to work on a $2,000 or $4,000 or $10,000, whatever the Macintosh amps cost these days. You'd be playing with another tube amplifier similar to my RCA set, and I would just simply pick the 2,000 Hertz and go from there. I wouldn't even be worried about trying to make the thing flat across 10 Hertz to 18 kilohertz or whatever. It just, it's a waste of time with those old amplifiers. You get them sounding as good as you can and you live with it. It's what, it is what that is. They are what they are. So I am going to solder these caps back in. I might take a quick look at the leakage on them. Why don't we do that just to see how bad they are. I'm sure the 8 microfarad that's in here is leaky. How bad the 20 microfarad capacitor is, I don't know. But let's just take a quick look. Okay, I have my solar connected to the 20 microfarad cathode bypass cap. And if I swing this around, if I don't knock the tripod over, and zoom in a little bit, there we go. Now I'll set this for leakage. This is a milliamp meter up here, presently set for 50 milliamps because the initial surge is going to be pretty high as it starts to charge. You saw it go up and drop. Right now it's at 100 volts. That cap is rated for 450 volts, so we'll roll this up to 400. There's 425, there's 450, and that cap is charging. You can see the current starting to fall off. Remember, we're on the 50 milliampere scale, so we're below 20 milliamps right now as it charges. It'll take a little while. I'm expecting some leakage here. That's a fairly old capacitor, 1956. but it's falling off at a respectable rate, and we're getting down now to 12 milliamperes and dropping. There's 10 milliamps. I'm going to give this some time because when the unit's turned on, the leakage will decrease as time passes, as the electrolyte reforms. 8 milliamperes. And let me give this, rather than sit here and just chew up time, I'm going to shut the camera off and I'll come back. About a minute and a half to 2 minutes has passed, and we're below 5 milliamps. I'm going to go to the next range, and that's 4.2 milliamperes, and it's still falling. I suspect if we sat here for another 10 minutes, we'd be down below a milliampere of leakage on that capacitor, which is perfectly acceptable for those old can caps. And remember, that cap is only running 210 volts. And I'm pushing 450, which is its limit. So let's bring it down to 200 volts and see what we end up with. So at 200 volts, the leakage on that cap right now is not even 500 microamps. So that capacitor at the 210 volts that it runs at is absolutely fine. Now I'll transfer this over. Let me put this back up on the 50 milliampere range, and we'll test this 8 microfarad cap. I won't even bother moving the camera. I'm just going to move it over to the other cap. This cap is rated for 350 volts, and it's operating at 100, excuse me. It's operating at 100 volts. So we're now connected on the 8 microfarad that's in the plate circuit. And I lied to you. The 20 microfarad operates at 100 volts, so it's even better. And we were testing at 200 volts. So the 20 microfarad only sees 100 volts. This cap sees 210 volts. And it's rated for 350. Where am I here? So we're at 200 volts already, and I'm not even seeing any current on there. Is there anything? Yep, there is. It's in the microamp region, and it's rated for 350. So if I go up to 300 volts, and you can see it's falling off. It's falling off. There's going to be some leakage. These caps are, let's see. Yeah, they're 60, almost 60 something years old at this point. But we're below a milliampere at 300 volts, and it only operates at 200 volts. And at 200 volts, it's not even moving the needle. Handful of microamperes at best. So that square wave distortion, or nonlinearity, is probably a better term, as far as I'm concerned, is to be expected on a simple circuit such as this. This is not professional high-end equipment. This was consumer grade test equipment, if you will. Let's see here. I'm going to shut this thing off so I don't get bit. We're going to put it on resistance instead of on leakage. That will discharge the cap. Okay, and for those interested, this is a sweep from one end of the dial to the other, and just look how uniform the amplitude stays. It's amazingly flat. They claim, I think, 1.5 dB from one end of the range to the other, and I believe it. It just is amazingly flat. This is the low frequency range, and you can see that action of that jitter is just the scope, but you can see the bounce a little bit due to the tube But if we come up to the higher frequency, you can see 1 or 2 bounces, it falls right in, bang bang. That's absolutely normal for this type of oscillator. It's just a characteristic of how they operate to balance out the level. But from one end of the range to the other, these things, it's just incredible. The output is extremely flat. I'm very impressed, actually. It certainly within, it's better than 3 dB. They say a dB and a half. Now this is the highest range, so it's not surprising that there's a little bit of amplitude change. But the lower ranges are just about perfectly flat from one end to the other. I love that little bounce. That's, again, perfectly normal. And, oh, I should mention, I forgot to mention that early on I tested, oh, look at that jewel light. I am such a sucker for anything with a red jewel on the front of it. Any of this old equipment that has one of those jeweled indicators, just, I fall in love with it instantly whenever I see it. It's just too much reflection in here. Those are beautiful. Where was I? Oh, I tested the tubes. Every one of the tubes in this unit, you'd swear just came out of a new old stock box. The emission is well into the good range. In fact, at the top end of the good range on every tube. No leaks, no cathode leaks to the heater, no shorts, no gas. They test, every tube in here tests like it's brand new. Just incredible. We've painted up the cabinet. As you can see, there's no more rust all the way around. We've got that gray hammered finish on here, which I think does a really marvelous job on this older equipment. It just dresses it right up. Hides a lot of sins. And that's the reason that they put the wrinkle finish on here in the beginning. Now, this isn't a perfect paint job. It could take, you know, I sprayed it outside. There's dust blowing around. There's a few specks here and there, but compared to what it was, it's gorgeous. It's just a shame about the front panel. People knock this stuff around and just have no respect for it whatsoever. I'm going to call this done. This was more of a play with it and get a little bit of education on how the thing worked. Show how to troubleshoot leaky capacitors, how they affect the bias, so on and so forth. Just a fun video, just something to play with. I picked this up as a toy. Not often you see these sets with all the original screws. For whatever reason, people take screws out and can't get them back in. Oh, and none of the screws are stripped. None of the holes are stripped, which is amazing. Half the time you find these sheet metal screws stripped out. They're all in good nick. Amazing. Just a lot of scratches on the face. For most of it's ready to go. The electrolytics are good, as you saw. Unless you're going to put a lot of hours on this, you could probably just leave them alone. That nice warm tube feeling. Love it. So that's it for this one, guys. Hope somebody found it useful. Hope somebody enjoyed the troubleshooting process of it, or portion of it. It was just interesting to show how the leaky capacitors affect the grid bias so badly. I can remember when I was very young, my father had a Fisher stereo system that they had purchased, spent a lot of money on, and 10 years on, the tubes, the finals were, the anodes were glowing red. Of course, you know, I was like 10, 12 years old at that point, and my father wouldn't let me play with it. And he, he didn't know how to fix it, so what he ended up doing was ripping the guts out, throwing them away, and turning it into a bookcase. He did that with a lot of things. I bought them a color TV when I went into the service and came home to find out that something had happened to it. And my father, rather than paying to have it fixed, threw the guts away and made a bookcase out of it. That was his thing. I was pretty upset, but, you know, what are you going to do? So, that's it for this one. I'm the Radio Mechanic. We'll see you again soon on the next one. Bye.